This is the second tutorial of Chapter 3 of the Digital Soil Mineralogy with our course, and we're building on what we did in the previous tutorial where we loaded the soil property and X-ray diffraction data um, and had a little exploration of it. And in this tutorial, we're going to move on to pre-treating the X-ray powder diffraction data prior to carrying out the machine learning. So to begin with, to recap, we had a little plot in the previous tutorial where we focused on the quartz peak at one of the sites. So we've got about 16 samples from one of the Sentinel sites in the data set, and this is focusing on the strongest quartz peak in the data. And it's from this you can see how there are small misalignments um, between the samples, and that's common with diffraction data because you've got these small effects of sample displacement that affect the peak positions in a very minor way, but it's important to account for these aberrations when doing any form of analysis on diffraction data, because even though they're minor, they do have quite a big impact on the analysis you're doing. So the first thing we're going to do is carry out an alignment using one of the alignment routines we've already covered in previous chapters. In chapter 1, we went through it, and it's also a very important part of full pattern summation that was covered in chapter 2. So here we're going to align all of these patterns to quartz. We're going to create a standard pattern of quartz from the RockChalk library and then align all the patterns to that standard, if you like. So here in this code, we're just creating an XY object from RockChalk. We're going to extract the 2 theta axis from RockChalk, and then we're going to extract the count intensities of the quartz pattern from RockChalk as well. And we'll first create a data frame from that, and then we'll make sure that it's as an XY object as well, just so we can have a look at it afterwards using the plot method for XY objects. So we plotted that, and this is the quartz pattern, the quartz standard that we've derived, and aligning all of the data within this multi-XY object, so all 935 patterns, is quite easy to achieve by using the align XY function. And if you apply it to a multi-XY object, it will recognize it as that, and it will do the alignment for all of those samples. So we just define the multi-XY object, XRPD, and then we're going to define quartz as the standard that we're aligning to. And you can adjust the 2 theta range that the alignment is conducted within. So here I'm going to apply it within between 10 and 60 degrees 2 theta. And we're going to allow a positive or negative shift of 0.2 degrees 2 theta. So if we run this, it will work through all 935 samples and align. Firstly, it will align all the samples to the quartz pattern. And then secondly, it will ensure that all the data are harmonized onto the same 2 theta scale, because in this alignment routine, little pieces of data are chopped off either end due to the way the shifting works, and then that will be by differing amounts depending on the alignment applied to the data. So then it needs to actually harmonize it all to the same 2 theta scale once they're all computed. And that can take a little moment to compute because we're working with such a large number of samples. So now that's just finished computing, we'll just replot the data in the same way that we did previously to get that plot of the quartz peaks for the Diddy site, which is what we were looking at here. So if we just plot that again, we can now see, oh, I haven't made this one interactive, but it doesn't really need to be, that those quartz peaks are now aligned really nicely. So that's the first pre-treatment step that we'll apply to the data. The next step we're going to work with is subsetting the data. Now, if I just plot this data again, but don't limit the x-axis, we should be able to see that there's quite a large tail on the left-hand side of the data. In this data set, you see this region here. So we're going to chop this out because it's largely due to the instrument as opposed to the sample. So we're going to reduce the 2 theta range to between 5 and 75 degrees. So that's simply achieved by using the subset function and defining the condition to subset by. So we're going to subset each of the items within this XRPD PT, so for pre-treatment, the PT stands for. We're going to subset each of the data frames within it by the 2 theta column, TTH. So now we have subset them. It didn't take long to compute. And if we plot the data now, well, without normalizing this time, we should be able to see that starting tail has now been removed. So far we've aligned and subset the data. The next thing we're going to do is mean center the data, because you can see from this plot here that there are shifts in count intensities so between the 16 samples, which doesn't necessarily relate to the sample composition. It often occurs due to the slightly different altered X-ray sources over time, especially when you're collecting large data sets such as this. You'll be recording data over months and potentially years. So there are deteriorations in the X-ray tubes that occur over that length of time. So if we mean center the data, which simply means subtracting the mean from each of the mean count intensities from each of the count intensity vectors, then we can account for this change in count intensities. To do that, we're just going to create a function called mean center, and it's going to be a function of x, where x is going to be one of these data frames. So it's going to be a 2-column data frame. First column is 2 theta, second column counts, and we want to apply the mean centering to the second column. So we're going to take the second column in this form, and we're going to make sure that the count intensities have their mean subtracted from them. So it's as simple as that, and then we're going to return x again. So we're just modifying the count intensities, but then returning the whole data frame. So we've created that function, and it's now in our environment up here. And in order to apply it to all 935 samples, we're just going to use lapply again. So it's just a case of defining the list you want to work with, and then the function. So that's mean centered everything here as well. So if we plot this now, we should see that change in background between the samples is now accounted for. So what we've done by this pre-treatment is try and minimize the sample independent variation and ensure that any variation within the diffraction data in the data set is purely due to the sample composition, as much as possible anyway. And we visualized just one site here using this form, but you could visually inspect all of the other 59 sites just to make sure that these pre-treatments have had the effect that we intended. In the next tutorial, we'll actually now move on to using the QBIST machine learning algorithm to predict total potassium from this pre-treated diffraction data.